Welcome back to the Explainer. Okay, let's dive straight into this, because if you've ever felt completely bogged down by a tangled, messy code architecture, the kind that just makes you want to pull your hair out, well, you are in exactly the right place. Today, we're focusing on fixing a massive headache in Haskell programming, though honestly, it's a headache that plagues developers across almost all languages. We're going to be looking at some really fantastic notes from a developer named Ang, who recently tackled a huge architectural flaw in their codebase. We're going to see how to transform a frustrating, repetitive anti-pattern into a remarkably clean, elegant solution.
Here is our roadmap for today. First, we'll look at the parameter drilling problem. Second, enter the ReaderT-pattern. Third, building the app environment. Fourth, running the monad. And fifth, we'll wrap up by discussing why you should prioritize readability over conciseness.
So, let's kick things off with Section 1, the parameter drilling problem.
Now, you might be wondering, what exactly is parameter drilling? Well, it's essentially manual dependency injection gone totally wrong. It happens when you have shared environment variables, configurations, or read-only states, and you're forced to manually pass them down repeatedly. From one function down to the next, and the next, and the next, it completely clutters up your code, it makes long-term maintenance an absolute nightmare, and frankly, it's just exhausting to write.
And this brilliantly illustrates what we're talking about. On the left side here, you've got the anti-pattern, manually passing these variables into literally every single function that might eventually need them. It's incredibly noisy. But over on the right, you see the ReaderT-pattern. Here we pass all of that shared environment in configuration implicitly through a monad. It's cleaner, it's quieter, and it lets your functions actually focus on what they're supposed to do, rather than acting as a glorified delivery service for your variables.
All right, let's move right along to Section 2. Enter the ReaderT-pattern.
Before we look at the exact code Ang wrote to fix this mess, we really need to set up the theoretical foundation. Now, we just mentioned the word monad, and look, I know if you aren't deeply entrenched in Haskell, that word can sound pretty intimidating, but let's demystify it right now. Just to recap, think of a monad simply as a context wrapper. That's literally it. For example, the maybe monad. It's just a context wrapper that yields either a just value or nothing. The IO monad is a context wrapper where the context produces side effects, like reading a file or printing something to the screen. We're basically just wrapping our code in a specific context.
A fascinating and honestly very pragmatic choice Ang made here was opting for a manual implementation. Instead of instinctively reaching for an external library like mt-li to simplify this process, which is what a lot of people do, they used the default transformer library that already comes bundled with GHC. This completely avoids external dependencies and keeps things incredibly straightforward. All of this foundational code is neatly grouped together in a single module called access-to-ebook.monad.
Which brings us to Section 3, building the app environment. Okay, enough theory. Let's actually step down into the concrete syntax. To pass our environment implicitly, we first have to define what that environment actually is. Here we have the AppEnv data structure, and it contains three key shared fields. First up is env-args, which captures the original arguments from the command line interface. Next is env-handle. This is the output handle, which defaults to standard error, or stder, making it absolutely perfect for logging and debugging. And finally, we have env-open. This is the actual function used to open the generated ebook file, defaulting to call process. So this single structure holds everything our app needs to know about the outside world.
With our data structure defined, we now have this wonderfully satisfying rhythmic blueprint for setting up our custom monad manually. Step 1 is exactly what we just did, defining AppEnv. Step 2 is wrapping the ReaderT-IO in a new type. Step 3 is creating some helpful little functions called ask and asks. And finally, Step 4 is building the run app executors. Let's look a bit closer at how Step 2 actually plays out in the code.
So check out our custom monad here, which we're just calling app. As you can see, we're wrapping a ReaderT that takes our AppEnv, the IO monad, and our value A. What does this mean in plain English? Well, it means our new app monad is essentially just the standard IO monad, but we've supercharged it with read-only access to our AppEnv. It's a really elegant setup.
But once you're actually inside that context wrapper, you need a way to grab the data out of it, right? That is where Step 3 comes in, our helpers. The ask function fetches the entire AppEnv environment all at once. The asks function, with an S at the end, allows you to pass in a specific field, like env-args, and it fetches just that specific piece of data. You can think of these as your hooks to easily pull exactly what you need out of that hidden implicit context.
All right, moving on to section 4, running the monad.
Let's see how all this theory builds into an actual executing application. Obviously, before we can run anything, we need a baseline state. The default end function takes those raw CLI arguments and builds the global environment from them. It sets up all those default values we just talked about. The standard system handles for logging, the process runners, the whole shebang. It basically prepares the world for our application to live in.
And here is how we actually execute the code. On the left, we have runapp. This takes those raw CLI arguments, builds that default environment, and then applies that environment detail to all the functions inside our app monad. But what if we want to test our code? We obviously don't want to use real system handles or process runners during a test, right? That's exactly why, on the right side, we have runapp with. This executor allows you to pass in a completely custom AppEnv instead of the default one. It is an absolute game changer for testing and mocking.
Finally, Section 5, readability over conciseness.
Okay, we've built the structure, we've set up our custom monad, and we are completely ready to refactor. But before we wrap up this explainer, I want to shift gears from the technical implementation into a really crucial coding philosophy that the author brought up. In Haskell, there's this concept known as eta reduction, or writing in a point-free style. Essentially, if the last argument on the left side of the equal sign is the exact same as the last argument on the right side, Haskell lets you just omit it entirely. It makes the code incredibly short. So it begs the question, should we omit these trailing arguments simply to make our code more concise?
Well, Ang strongly argues against doing this. Let's compare the two approaches. On the left is the eta-reduced point-free style, and yes, it is very concise, but it's also entirely implicit. This is often referred to as Academy Haskell. You know, the kind of code that looks really clever written out on a chalkboard. But on the right, we have explicit arguments. You write out exactly what is being passed in. This is industrial Haskell. It prioritizes readability and long-term code maintenance over just trying to look clever. Because let's be real, when you're working in a complex, real-world code base, knowing exactly what arguments a function takes at a mere glance, that saves hours of frustrating debugging.
The philosophy behind the Ada programming language puts it perfectly. Readability is more important than conciseness. By choosing the explicit industrial style of the ReaderT-pattern, we are building a code base that's designed for the long haul. It perfectly primes us for Ang's upcoming refactoring lesson. So, I'll leave you with this to chew on. Is your code written to look clever on a whiteboard, or is it written to actually survive in the real world? Thanks so much for joining us on this explainer, and we'll see you next time.